And here we go. The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I will respond as soon as I can. All right, today, eventually, we're going to go on to section 9.3, but first I have at least a couple of questions from 9.2. So we're going to look at those. All right. First of all, this is number 30. It says, use rational exponents to simplify the radical. All variables represent positive real numbers. So what they want us to do is to take this radical, which is the 12th root of x squared y squared, convert it into exponential form. So that would become x squared y squared to the 1/12th power. Simplify it down. So that would become x squared to the 1/12th, y squared to the 1/12th, which is x to the 2/12ths, y to the 2/12ths, which is x to the 1/6, y to the 1/6, and then put it back in radical form. So I'm going to go back up here. We could write that as xy to the 1/6, which would then become the 6th root of xy. Now, the person who asked for this, which is here today, I think the problem was in the notation, because I looked at your previous answers and I think one of them was this. And the problem is you've got to use the right, over on the right side of your homework problems, there's a screen that you can access. And I think there's a screen that has a little box and then like that. So you need to get that 6 inside the box as the index. When it's over here on the outside, then it's like a regular 6 as a multiplier. So take a look at that. If you still have issues, let me know, but I think that might have been the problem. Anyway, so that's the correct answer there. And then let's go on and take a look at problem number 37, also from 9.2. And that says, simplify the expression. The variable represents a positive real number. We have t to the 4/3 power, parentheses, t to the 8/3 power, plus t to the negative 4/3 power. So we're going to distribute the t to the 4/3 power. First of all, I'll get the product, t to the 4/3 power times t to the 8/3 power. Then plus the product, t to the 4/3 power times t to the negative 4/3 power. Now, we have a situation here and here where we are multiplying two powers with the same base, t being the common base. In that case, we add the exponents. So this first one would be t to the 4/3 plus 8/3, which is t to the 12/3, which is t to the 4th power. The second one would be t to the 4/3 plus negative 4/3, which is t to the 0 power, which is 1. So there is your final answer, t to the 4th power plus 1. Any questions from anybody about that problem? All right. Do you have any other questions from this assignment before we go on to section 9.3? All right, and here we go. Now, we're going to look at two rules in section 9.3, and really they are just radical form of exponential rules. The first one is this. If we have a product, let's say a times b, raised to a power, we'll say n, we then attach that outside power to each factor inside. So we get a to the n, b to the n. And we looked at this yesterday at the beginning of class when I went through and was looking at these rules. Now, let's say we had a, b, the quantity, raised to the power 1 over n. That would still be an exponent. That would be a to the 1 over n, b to the 1 over n. Do you have any questions about how I got there? Well, now let's take that equation and let's rewrite it in radical notation. It would look like this. The nth root of the product AB equals the nth root of A times the nth root of B. So what that says, if I have a product as a radicand inside, I can split apart each separate factor and take the nth root of that. So for instance, let's say I've got the cube root of 8x cubed. I could rewrite that as the cube root of 8 times the cube root of x cubed. And from there, I could go on and simplify it. Now, we actually already used this rule a little bit yesterday, though it wasn't officially talked about. But anyway, so if I've got a product inside of a radical, I can break it apart into separate factors, each to the same, each with the same index, okay, or the same root. All right, that's one rule. There's a second rule that says if you have a quotient raised to a power, you can attach that power to both the numerator and denominator of the quotient. Okay, so we could also write that like this and say, what if the exponent was 1 over n? Then we'd get that. Okay, translating that into radical notation, we've got the nth root of the quotient, which becomes the nth root of the numerator over the nth root of the denominator. So if we have a quotient inside of a radical, we can take the numerator, take the root of it, divided by the same root of the denominator. Okay, so those are just variations of rules that we've already, that come from the past. Okay, now, let's see here. We're going to look at something called simplifying a radical. And the final form might not look simpler to you. So let me kind of define what we mean by simplifying a radical. If we have, let's say, for instance, the square root of 28. If we want to simplify that radical, that means we want to get everything that's on the inside outside, at least as much of it as we can. Now, before we go on further, another thing I want to point out, if we have the square root of 3 squared, that's 3, right? The square root of 27 squared is 27. The square root of 1.382 squared is 1.382, because the 2 implied as the index and the 2 as an exponent have the effect of reducing out. Okay? What if I have the cube root of 72 cubed? Well, that's going to be 72. What about the fifth root of 1004 to the 5th power? That would be 1004, because in each case, the index and the exponent would reduce out, okay, or sort of undo each other. Now, that leads us.
So what if we had, like, since it was, if it would have had 4 instead of 3?
Where? Here?
Yeah.
Like if this had been a 4?
Yeah, if 72 fourths instead of thirds.
So this was to the 4th power.
Yeah.
But was this also a 4th power?
No, if it would have been
okay, okay. We're gonna get there eventually. Yes, it's coming.
Okay.
But what I'm trying to drive home is this idea. The nth root of a to the n equals a if a is greater than or equal to 0. In other words, the index and the exponent will reduce out as long as a is positive. Now, a could be negative, but then it would only be real if n was an odd root, okay? So using that idea, let's go back to this square root of 28. What is the implied index here? It's a 2. So we're looking for square factors inside that we can unsquare and kick outside. So for instance, the square root of 28 could be written as the square root of 4 times 7, right? 4 times 7 is 28. Using one of these new rules we looked at, we could write that as the square root of 4 times the square root of 7. Since I've got a product here, I can split up each factor, again, with the same index of an implied 2. Now, what is the square root of 4? Well, that's a 2, plain old 2, and it's no longer inside of a radical. The square root of 7 doesn't simplify further, so here's my final answer. So the square root of 28 simplified becomes 2 square roots of 7. Now, it doesn't look simpler, but definition of simplified would be getting everything outside of the radical that you can. So reducing the size of the radicand insides from a 28 down to a 7. All right, are you okay with what happened there? Any questions? All right, let's continue with that idea. Let's say I've got 9 square roots of 54. Since the implied index is a 2, I want to find factors inside that are squares. Well, let's see. 54 is what? 2 times 27, which is 2 times 3 times 9. So I could rewrite this as 2 times 3 times 9 inside, okay? Which I could rewrite as 9 times the square root of 2 times the square root of 3 times the square root of 9. Now, eventually I'm going to shortcut all of this. So if you're sitting there going, you know, you don't have to do all that, blah, 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 be patient. We'll get there. But I want to make sure everybody understands what's going on. Okay, so do you see how I got from 54 to that to this? Now, 9 times the square root of 2 times the square root of 3. Oh, the square root of 9 is a 3. So I can undo that square root of 9, kick it outside where it's a 3, put these together, 27 square roots of 6. So 9 square roots of 54 becomes 27 square roots of 6. Again, I've simplified the radical. I've reduced it down from a 54 to a 6. Any questions there? All right.
So you don't add the 9 and the 3, you multiply it.
Right, this is all being multiplied.
Okay.
Okay, now let's take a look at the cube root of 40. Now my index is a 3 instead of a 2. So I'm looking for cubes inside. Okay, well, I happen to know that 40 is 8 times 5 and 8 is a cube. So I could just go in here and say that's going to be that. And then the cube root of 8 is 2. So I get 2 cube roots of 5. Okay, now let's go back and let's do that a bit slower. Let's say that off the top of your head, you don't recognize that 8 is a factor of 40 and 8 is also a cube. You could do it this way. Well, let's make that a little nicer. You could take 40 and break it down into prime factors. Okay, so 40 is equal to 2 to the 3rd power times 5. So now I'm going to rewrite this as 2 to the 3rd power times 5. Okay, I could split that up. the cube root of 2 cubed times the cube root of 5. Well, here is that the nth root of a to the n is a, so the cube root of 2 cubed is 2. That 2 is outside of the radical. The cube root of 5, I can't do anything with that, so there's my final answer. So if you can't see where to go, prime factoring will help you to see what's there. Any questions about that one? All right, let's take a look at the fourth root of 32. So now my index is a 4. I'm looking for factors inside that are powers of 4. Again, I happen to know that 16 is 2 to the 4th power, but that may not be common knowledge. So let's figure it out. Let's see, that, and that, and that. Oh, so 32, written in prime factored form, is 2 to the 5th power. But my index is a 4. So what I'm going to do is I'm going to think of this as 2 to the 4th power times 2 to the 1 power. So this is going to be the 4th root of 2 to the 4th power times 2 to the 1 power. I could rewrite that as the 4th root of 2 to the 4th times the 4th root of 2. I can drop that 1 because it's implied. So I've got 2 to the 4th power and leftovers. What is the 4th root of 2 to the 4th power? What is the nth root of a to the n? It's a, or in this case, 2. Tell you what, let's take a look at this in exponential form, just in case you're not seeing it. If I rewrote that in exponential form, wouldn't that be 2 to the 4/4 power? Because that would be the top of the exponent and that would be the bottom, but that's 2 to the 1, which is 2. So in effect, the exponent in the index reduce out. Now the 4th root of 2, I can't do anything with, so there's my final answer. The 4th root of 32 becomes 2 4th roots of 2. Okay? All right, let's see here. Oh, and let's see. Anaya, I think it was you that asked this earlier, when, what if the power inside was larger than the power outside? And that's kind of what's happening here. It's like the 4th root of 2 to the 5th, where this is higher than that. So I split it apart into the 2 to the 4th and 2 to the 1 and just deal with that one. Does that make sense?
Yeah.
Okay, good, good. All right. We have the square root of 50x squared. It says, simplify each radical expression. All variables represent positive real numbers. That's saying we don't have to worry about absolute value because they're telling us up front the variables are all positive. Okay. Now, my index is an implied 2, so I want squares. Well, 50 is 25 times 2, 25 being a square, and then I've got x squared. Okay. Now I'm going to start to shortcut things. In the past, I would have rewritten this, and this, and this, and then done this, and then done that. Follow what I did there? I'll take that as a yes. Yeah. So what I'm going to do now is say, why don't we just do it a piece at a time and say, okay, the square root of 25 is 5 outside. The square root of 2 I can't do anything with. The square root of x squared is x outside, so I get 5x square roots of 2. And that's how I can do that step a little bit more efficiently. Okay? Any question about that? All right, here comes another one. The square root of 75 b to the 8th c. Okay, now 75 b to the 8th c. 75 is 25 times 3. 25 is a square. I could take b to the 8th and make it b squared times b squared times b squared times b squared times c. So I got all these squares. Okay, so this is the long way again. We'll do it this way first. So 25 times 3 times b squared times b squared times b squared times b squared times c. So I took b to the 8th and wrote it as b squared. Taking the square root of 25, I get 5. The square root of 3 doesn't get me anywhere. The square root of b squared is b. 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 And I've got 3c left inside. So I've got 5 b to the 4th square roots of 3c. Now, that's doing it the long way. But consider this. The square root of b to the 8th power. There's an implied 2 there, right? If I wrote this in exponential form, it would be b to the 8 over 2 or b to the 4th power. What if I had the square root of b to the 6th power? That would be b to the 6 over 2 or b to the 3rd power. My point is this. If this exponent is larger than the index, but it's a multiple of the index, b squared, b to the 4th, b to the 6th, b to the 8th, I can still simplify it down without having to break it up into individual pieces. Okay? So in other words, the quicker way of doing this, let's see here, would be to think of this as what? 25 times 3 times b to the 8th times c. Square root of 25 is 5. Square root of b to the 8th is b to the 8 divided by 2 is 4. And I've got 3c left inside. Does that make sense?
Yes.
All right, let's say we had this. Let's say we had the square root of 75 b to the 9th times c. Then I would rewrite it as 25 times 3 times b to the 8th times b times c. So I take the largest power of b that I could, that's a multiple of the index, so b to the 8th, and then I've got that one extra b there. So this is a 5, this is a b to the 4th, and I've got 3bc left inside. Okay? So I'm going to take out as many of the index as I can, and then leftovers. And the leftovers are stuck inside forever. Sob. Okay. Let's see here. How about this one? The 5th root of 64 x to the 10th y to the 5th. 64 is 8 times 8 is 2 times 2 times 2 times 2 times 2 times 2 is 2 to the 6th power. But I'm going to write it as 2 to the 5th power times 2 to the 1 power. Why? Because I want to match my index or multiples of the index. So now this becomes the 5th root of 2 to the 5th times 2. Oh, x to the 10th. 10 is a multiple of 5. Excuse me, y to the 5th. Okay. So now, what's the 5th root of 2 to the 5th? It's 2 on the outside. The 5th root of 2 isn't going anywhere. What's the 5th root of x to the 10th? That's x squared. 10 divided by 5 is 2. And the 5th root of x to the 5th, excuse me, y to the 5th is y. And I've still got the 5th root of 2 left inside. So there's the idea. Any questions about that problem? All right. Let's see here. The square root of 147 a to the 5th power. 147. I think 7 goes into that. Let's see, how many times? Let's go. 147 divided by 7 is 21. So this is 7 times 21, which is 7 times 7 times 3, which is 7 squared times 3. Okay. So I'm going to write that as 7 squared times 3. Now, a to the 5th power, I'm going to write it as a to the 4th times a to the 1 power. Why a to the 4th? Because 4 is a multiple of the implied index of 2, so I can undo a to the 4th power by taking a square root. Okay, so what's the square root of 7 squared? That's a 7 on the outside. The square root of 3 stays inside. The square root of a to the 4th would be a squared, and the square root of a stays inside. So I have 7a squared times the square root of 3a. Any questions there? The biggest mistake that students make with these problems, and it doesn't actually pertain here because the index is a 2, so you don't have to put anything there, but there'll be something where the index is a different number and they'll forget to put the different index in there. So be careful of that. I've had students ace this test, but for that one little piece. Let's take a look at this one. This will make more sense. The cube root of 280 a to the 5th, b to the 6th. All right. So I'm going to take 280 and break it down. That would be 28 times 10. 28 is 4 times 7. 10 is 2 times 5. 4 is 2 times 2. So breaking it down into prime factors, I get that. Now, my index is a 3, so I've got 2 to the 3rd. That's good. So I've got the cube root of 2 to the 3rd power times 5 times 7. A to the 5th power, I'm going to take an a cubed out and have an a squared left over. B to the 6th power, 6 is a multiple of 3, so I'm going to leave that as b to the 6th power. Okay, so I want my exponents to match the index, the 3, or be multiples, like as in the 6. Okay, so here we go. What's the cube root of 2 cubed? It's 2 outside. The cube root of 5 isn't going anywhere. The cube root of 7 isn't going anywhere. The cube root of a cubed is a. The cube root of a squared isn't going anywhere. The cube root of b to the 6th is b squared. So I've got 2ab squared times the cube root of 35a squared. And right there, don't forget it's a 3. It's not a 2. And notice that I multiplied the stuff back together that was left inside the 5 and the 7. You okay with that? All right. Next problem. Let's say we've got the square root of a fraction. It says simplify each radical expression. All variables represent positive real numbers. I could rewrite that as the square root of 3. Oops, got ahead of myself there. Over the square root of 4. That was that rule we looked at the beginning of class here. If you have the a radical that's a fraction, you can separate the numerator from the denominator, separate radicals, okay? Well, the square root of 3 I can't do anything with, but the square root of 4 equals 2. So that's another way we simplify the radical, by getting rid of a denominator that's inside. Any questions there? Okay, let's take a look at, let's see here. This one, the 5th root of 2 over 243. So that's going to be the 5th root of 2 over the 5th root of 243. Well, I can't do anything with the 5th root of 2, but 243, let's see, 2 doesn't go in, but 3 goes in 81 times, and that's 9 times 9, And 3 or 9 is 3 times 3. So we got 3 to the 5th power. Oh, okay. So I've got the 5th root of 2 over the 5th root of 3 to the 5th power, which is the 5th root of 2 over what's the nth root of a to the n if a is greater than or equal to 0. It's a. So we get a 3 because the 5th root of 3 to the 5th power is 3. You okay with that? Well, I'll take that as a yes. Okay, now, just like we can take a fraction inside and split it up into a numerator and a denominator, we can go the other direction. Let's say we've got the square root of 500 over the square root of 5. So we have a fraction of two radicals. They have the same index, so we could now put them as a single radical written with a fraction inside. Why would I want to do that? Because now inside I can reduce that down. 500 divided by 5 is 100, and the square root of 100 is 10. We okay with that? Questions there? All right.
So we don't have to break it down if we don't want to. We can just do it like this and not separate both of them then, right? Or do we have to do that with
Yeah.
somehow?
Did you want to take these and break it apart, you mean?
Yeah.
Let me do it the other way, and then I think it'll convince you that you want to do it this way. Okay.
No, I get it. That's what I was asking. Like, if
Yeah.
we don't have to do it the other way, we can do it this way.
I wouldn't show you something that I didn't want you to do. That would be that would not be nice.
Thank you.
You're welcome. Okay.
What if it was, Mayo?
What?
What if it was two numbers that don't go into each other well? Like, does it matter if we get decimals and stuff? Is that fine? Or
The ones that you're going to deal with, they're going to be nice. The one,
okay.
like, so let's say you had the square root of 48 over the square root of 17.
Yeah.
That's a Math 95 problem. We'll spare you the pain. Okay.
Okay.
Okay. Let's see here. How about this one? The cube root of 64y to the 8th power over the cube root of 8y squared. The question people usually ask is, what if the indexes or the indices aren't the same? And I'd say that's a Math 141 problem. We won't go there either. Things could get worse, but we won't torture you that much. All right, so this could become the cube root of 64y to the 8th over 8y squared, okay? But inside, I can reduce that down to 8y to the 6th. 64 over 8 reduces to 8 over 1. Y to the 8th over y squared is y to the 6th. Okay?
Yep.
What's the cube root of 8? 2. What's the cube root of y to the 6th? Y squared. No radicals. It's all outside. All is good with the world. Righty?
Mm-hmm.
Okay, now, let's say we've got 2x plus 3x. Those are called like terms. What's 2x plus 3x?
5x.
5x. Let's say I've got 2 square roots of 11 plus 3 square roots of 11. Those are called like radicals. What would 2 square roots of 11 plus 3 square roots of 11 be?
5 square roots of 11?
Yeah. Some of you were overthinking this. 5 square roots of 11, okay? All right, now, let's say we've got 11 square roots of 3 plus 2 square roots of 3. That would equal
13 square roots of 3.
Okay. Let's say we've got 30 times the cube root of 6 minus 10 times the cube root of 6. What would that be?
20 to the cube root of 6?
Yeah, 20 cube roots of 6. Okay.
Yeah.
Right now, let's say we've got 9 plus the square root of 45 plus the square root of 20 plus 16. And it says simplify by combining like radicals. What we need to do is take each separate term and simplify it as much as possible first. Well, 9 is going to stay 9 and 16 is going to stay 16. But I could take the square root of 45 and write it as 3 square roots of 5. 45 is, 9 times 5, square root of 9 is 3 outside. Okay.
Mm-hmm.
I could take 20 and write it as 4 times 5. The square root of 4 is 2 outside square roots of 5. So this simplifies to that. This simplifies to that. But look at those. Those are like terms, as are those. So I've got 9 plus 16 is 25 plus 3 square roots of 5 plus 2 square roots of 5 is 5 square roots of 5. Now, I can't add the 25 and the 5 square roots of 5 because those are not like terms. Okay. So the key to this problem is simplifying each radical as much as possible first, and then identifying like radicals so that you can combine them. We all right with that?
Yep.
Okay, let's take a look at another one. The square root of 20 plus the square root of 125 minus the square root of 80. Okay. I could rewrite the square root of 20 as the square root of 4 times 5. The square root of 4 is 2, so I get 2 square roots of 5. I could take the square root of 125 and write it as 25 times 5. And again, I'm kind of speeding up the process here. If you're not quick to see that 125 is 25 times 5, then you go over here and you break it down, whatever. But I'm kind of skipping that step right now, just because I want to emphasize the simplified form. What's the square root of 25? That's 5. Square root of 5 still inside. 80 would be 16 times 5. The square root of 16 is 4, so I get 4 square roots of 5. So I simplified each radical as much as I could. Notice now they're all like radicals. 2 of something plus 5 of something is 7 of something. 7 minus 4 is 3 of something, the something being the square root of 5. All right with that?
So you don't add the square roots of 5, just it's 1 square root of 5?
Well, let me ask you this. Was 2x plus 3x 5xx or just 5x?
5x.
So if you've got 2 dogs plus 3 dogs, do you have 5 dogs or do you have 5 dogs?
You have 5 dogs.
So you got 2 of something plus 5 of something minus 4 of something would be 3 of something, the something being the square root of 5.
Okay.
And that question gets asked a lot, so don't be surprised. Okay, let me do one more here. 23 fourth roots of 3 plus the 4th root of 48. Well, if I look at that first expression, I can't really do anything with the 4th root of 3. But 48 is 2 times 24, 2 times 2 times 12, 2 times 2 times 2 times 6, 2 times 2 times 2 times 2 times 3. Oh, it's 2 to the 4th times 3. Aha. So this would be 23 fourth roots of 3 plus the 4th root of 2 to the 4th times 3, which is 23 fourth roots of 3 plus, what's the 4th root of 2 to the 4th? It's 2 outside. Okay, so the 4th root of 2 to the 4th is 2 on the outside. Now I've got like radicals. 23 of something plus 2 of something is 25 of the something, and the something being the 4th root of 3. Okie dokies. Let's see here.
Will we ever get some that have the root different than the other root? Like let's say 23, 4 roots of 3, and then 3 roots of, cube root of 48.
Welcome to Math 95. Yeah, we do that there. So again, 95 takes some of these concepts a bit further than we do in Math 93, and that's one of those things.
Okay.
Tell you what, let's look at one anyway, just to give you an example. So here we have the square root of 80m minus the square root of 128m plus the square root of 288m. Okay, now 80 is 16 times 5. So this becomes 4 square roots of 5m. 128 is 64 times 2m. So this becomes 8 square roots of 2m. 288 is 144 times 2m, which becomes 12 square roots of 2m. And again, I kind of went through this quickly, but I got squares and leftovers. Notice these two are alike, but this one isn't. So we get 4 square roots of 5m plus 4 minus 8 plus 12 plus 4 square roots of 2m. And those won't combine any further. So there's kind of what you were asking about. Okay.
Okay.
Not much more difficult. Just, if you're expecting them all to go together and then they don't, sometimes people are like, well, did I mess up? Nope. Okay. Well, that's it for today. So let's stop the recording.